What if the moment you stop eating is not the moment your body begins to fail, but the moment it finally switches on a deeper survival system? This question challenges nearly everything modern nutrition has taught us. We are conditioned to believe that missing meals is dangerous, that hunger equals breakdown, and that the body requires constant feeding to function. But biology tells a far more complex and far more unsettling story. This video is not about encouraging extreme fasting. It is not medical advice. It is an examination of what science has observed when food disappears for an extended period of time. Because when researchers look beyond fear and habit, they find something unexpected. The human body does not immediately weaken without food. It reorganizes, it adapts, and it activates metabolic programs that remain dormant in a constantly fed state. From an evolutionary standpoint, this makes perfect sense. For over 99% of human history, regular meals did not exist. Food availability fluctuated, scarcity was common, and survival depended not on constant intake, but on biological flexibility. The body that could not function without frequent feeding did not survive long enough to pass on its genes. What survived instead was a metabolism capable of switching modes. So what actually happens inside the body when eating stops? The answer begins quietly. In the hours following your last meal, nothing dramatic appears to change. Blood glucose remains stable. Cells continue receiving energy. Hormones maintain their usual rhythms. From the outside, it looks as though the body hasn't noticed the absence of food at all. But internally, a calculation has already begun. During this initial phase, the body relies on glucose from the most recent meal. Excess glucose has been stored as glycogen in the liver and muscles, an energy reserve specifically designed to bridge short periods without food. Insulin remains present, directing glucose into cells and signaling that energy is still available. From a scientific perspective, this stage is not fasting. It is simply the tail end of digestion. This distinction matters because many people interpret early hunger as a sign of danger. In reality, early hunger is largely neurological and behavioral, not metabolic. The stomach may feel empty, but cellular energy levels are still sufficient. What the brain is responding to is interruption, an absence of expected signals. Habit withdrawal can feel intense, but intensity does not equal harm. As time passes, subtle changes begin to accumulate. Insulin levels gradually decline. This is not dysfunction, it is communication. Lower insulin tells the body that incoming energy from food can no longer be assumed. In response, the metabolic system starts shifting priorities. Glycogen stored in the liver becomes the primary source of glucose, released carefully into the bloodstream to maintain blood sugar within a narrow, safe range. This process is highly regulated and remarkably efficient. Between 12 and 18 hours after the last meal, liver glycogen stores begin to fall significantly. This is a pivotal biological moment. The body can no longer rely exclusively on carbohydrate reserves. A new strategy becomes necessary. At this point, the question is no longer whether the body will adapt, but how. From an evolutionary perspective, this transition is not a crisis, it is expected. When glucose availability declines, fat tissue, often misunderstood as passive storage, becomes metabolically active. Fatty acids are released into circulation, and the liver begins converting them into ketone bodies. These molecules are not metabolic waste. They are a deliberate alternative fuel particularly suited for long-term energy demand. This metabolic shift, however, is not instantaneous. Around the 24-hour mark, many people experience headaches, irritability, fatigue, or mental fog. These sensations are frequently misinterpreted as signs that something is going wrong. In fact, they reflect a temporary mismatch between fuel supply and fuel utilization. The brain, which prefers glucose, has not yet fully adjusted to using ketones efficiently. Importantly, this discomfort does not signal damage. It signals transition. As ketone levels rise, neurons begin to adapt. Ketones provide a more stable energy source than glucose, producing fewer fluctuations and less oxidative stress. Research has shown that ketone metabolism can reduce inflammatory signaling in the brain and support mitochondrial efficiency. This is why, after the initial adjustment period, cognitive function often stabilizes rather than deteriorates. At this point, it's worth pausing for a moment. If you're finding this breakdown helpful, consider subscribing to the channel. This channel exists to move past fear-based narratives and translate complex biology into clear, evidence-driven understanding without hype and without oversimplification. By the end of the first full day without food, the body has not shut down. It has restructured. Energy production shifts from reliance on constant intake to controlled use of internal reserves. Hormonal signaling adjusts to protect essential systems, and perhaps most importantly, the body demonstrates a fundamental principle of human physiology. Hunger alone does not equal harm. What follows in the next stages goes beyond fuel substitution. As fasting continues, the body begins activating processes that rarely occur in a constantly fed state: cellular recycling, immune modulation, and metabolic optimization. These mechanisms are not speculative, they are measurable, well-documented, and deeply rooted in evolutionary biology. In the next part of this video, we'll examine what happens between 24 and 48 hours when the body fully commits to fat-based metabolism and activates autophagy, a cellular cleanup process directly linked to aging, inflammation, and disease risk. This is where fasting shifts from the absence of food to an active biological state. As the body moves beyond the first 24 hours without food, the metabolic story changes in a fundamental way. This is no longer a short-term adjustment. The body begins to fully commit to an alternative operating system, one designed not for abundance but for endurance. By this point, insulin levels remain consistently low. This single hormonal shift has wide-reaching consequences. Low insulin removes the signal to store energy and instead unlocks access to long-term reserves. Fat tissue now becomes the primary fuel source, releasing fatty acids steadily into the bloodstream. The liver continues converting a portion of these fatty acids into ketone bodies, increasing their availability to the brain and other organs. This stage is often described in research as metabolic flexibility in action, the body's ability to switch from carbohydrate dependence to fat-based energy with minimal disruption. In metabolically healthy individuals, this transition is not only possible, it is efficient. Energy levels begin to stabilize. The sharp fluctuations associated with glucose rise and crash fade. What replaces them is a slower, steadier form of fuel delivery. At the cellular level, something far more significant is unfolding. With digestion paused and nutrient intake temporarily absent, the body reallocates resources. Energy that would normally be spent processing food is redirected toward maintenance and repair. One of the most important processes activated during this window is autophagy, a regulated cellular recycling system that identifies and breaks down damaged or dysfunctional components within cells. Autophagy is not a response to starvation in the way it is often portrayed. It is a quality-portrayed mechanism. Cells continuously generate waste, misfolded proteins, damaged mitochondria, and molecular debris that accumulate over time. Under normal feeding conditions, autophagy operates at a low baseline level. During extended fasting, its activity increases markedly. This increase is not random. Research shows that autophagy preferentially targets components that compromise cellular efficiency. Dysfunctional mitochondria, which produce excessive oxidative stress, are dismantled. Protein aggregates that interfere with cellular signaling are broken down. The resulting materials are reused to build new functional structures. From a biological standpoint, this is not destruction, and it is renewal. This is why scientists often describe autophagy as one of the body's most powerful anti-aging mechanisms. It does not make cells immortal, but it improves their resilience. By clearing internal damage, cells function more efficiently and respond better to stress. Importantly, this process is tightly regulated. The body does not indiscriminately break itself down. It selectively optimizes. As autophagy ramps up, many individuals report a noticeable shift in how they feel. hunger often diminishes rather than intensifies. This surprises people who expect appetite to increase with time. In reality, appetite is heavily influenced by insulin and glucose dynamics. As those stabilize at low levels, hunger signaling often quiets. What remains is not weakness, but alert calm. Meanwhile, the brain continues adapting to ketone metabolism. Ketones cross the blood-brain barrier efficiently and provide a reliable energy source. Unlike glucose, they generate fewer reactive oxygen species during metabolism. This reduces oxidative stress in neurons and supports mitochondrial health. As a result, mental clarity often improves rather than declines. At this point, it is critical to emphasize context. The experiences described here are observations from controlled studies and metabolic research. They are not guarantees, and they do not apply uniformly to all individuals. Health status, metabolic flexibility, and underlying conditions all matter. This channel exists to explain mechanisms, not to suggest that prolonged fasting is appropriate or safe for everyone. If you value evidence-based explanations like this, subscribing to the channel helps support content that prioritizes clarity over sensationalism. Understanding biology should empower informed thinking, not pressure behavior. By the 48-hour mark, the body has largely completed its transition into ketosis. Fat-drained fuel dominates energy production. Blood sugar remains stable without external input. Growth hormone levels rise significantly, a response that helps preserve lean tissue and support cellular repair during energy scarcity. This hormonal environment reflects an ancient survival state, one optimized to protect critical systems while resources are limited. Another system undergoing quiet but meaningful change is the immune system. During prolonged fasting, immune cells are not destroyed indiscriminately. Instead, older, less efficient immune cells are more likely to be cleared through autophagy. This creates space for renewal once feeding resumes. Research suggests that this process may help recalibrate immune function, though it is an area of ongoing study. Inflammatory signaling throughout the body also tends to decrease during this phase. Lower insulin and reduced glucose variability contribute to this effect. Chronic low-grade inflammation, which is strongly associated with metabolic disease, thrives in constant energy surplus. In contrast, temporary energy scarcity appears to shift the body toward conservation and repair. Hence, it is important to recognize what this state is and what it is not. This is not a state the body is designed to remain in indefinitely. It is a temporary adaptation, triggered by the absence of food, and resolved when feeding resumes. The benefits observed are tied to controlled duration and appropriate recovery, not prolonged deprivation. As the second day without food concludes, the body is no longer reacting to the absence of meals. It is operating according to a different internal logic. Energy is conserved and distributed efficiently. Cellular maintenance is prioritized. Hormonal signals favor preservation over growth. The system is quiet, focused, and remarkably coordinated. In the next segment, we will explore what happens as fasting approaches the 72-hour mark. This is where some of the most dramatic biological changes occur, including immune system restructuring and stem cell activation. These processes highlight the extraordinary capacity of the human body to reorganize itself, not through constant stimulation, but through strategic rest. As the body approaches the 72-hour mark without food, the metabolic process enters its most stabilized and internally coordinated phase. At this point, the body is no longer reacting to the absence of meals. It has adjusted its internal priorities and settled into a temporary physiological configuration, optimized for conservation, repair, and efficiency. Energy production is now firmly rooted in fat metabolism. Ketone levels remain elevated and stable, providing a consistent fuel supply for the brain and other organs. Blood glucose is maintained within a narrow range without external input. Insulin remains low, reducing the signals associated with energy storage and growth, and reinforcing those associated with preservation and maintenance. One of the most significant biological changes observed during this period involves the immune system. Rather than remaining static, immune activity undergoes selective restructuring. Research indicates that during prolonged fasting, older and less efficient immune cells are more likely to be cleared through autophagy. This process does not represent immune suppression in a pathological sense. Instead, it appears to be a recalibration mechanism, reducing cellular inefficiency and preparing the system for renewal once nutrient intake resumes. In experimental models, fasting periods approaching 72 hours have been associated with activation of stem cells involved in immune regeneration. This does not imply that fasting universally strengthens immunity or serves as a therapeutic intervention. Rather, it highlights the immune system's capacity to reorganize under specific metabolic conditions. The key insight is adaptability, not enhancement. At the systemic level, inflammatory signaling throughout the body tends to decline. Lower insulin concentrations, reduced glucose variability, and the absence of continuous digestive activity collectively contribute to this shift. Chronic low-grade inflammation, which characterizes many metabolic and autoimmune disorders, thrives in environments of constant energy surplus. Temporary energy scarcity appears to interrupt this pattern, encouraging the body to shift from constant activation towards strategic restraint. The gastrointestinal system also experiences a notable period of rest and recalibration. Digestion is among the most energy-intensive processes in the body. When it pauses, cellular repair within the intestinal lining becomes more prominent. Tight junctions between intestinal cells, critical for maintaining barrier integrity, may strengthen during this time. The liver, relieved of constant nutrient processing, redirects capacity toward detoxification and metabolic housekeeping. Simultaneously, the gut microbiome begins to adapt to the absence of incoming dietary substrates. Microbial populations shift in composition and activity, reflecting the new metabolic environment. While these changes are complex and still under investigation, they reinforce a central physiological principle. Periods of reduced input allow internal systems to reorganize and rebalance. Neurologically, the brain continues operating in a state of metabolic efficiency. Ketone-based energy production generates fewer reactive oxygen species compared to glucose metabolism, reducing oxidative stress in neurons. Cortisol, the body's primary stress hormone, often stabilizes rather than escalating. Growth hormone remains elevated, supporting tissue preservation and repair. Hunger signaling is typically subdued, replaced by a state often described as calm alertness. It is important to emphasize that this state is neither pathological nor idealized. It is a temporary adaptation, evolved to support survival during scarcity. The human body is not designed to remain indefinitely in this configuration. The benefits observed during this phase depend not only on the absence of food, but on the body's capacity to exit the state appropriately. This transition, known as refeeding, is a biologically sensitive phase that carries as much significance as the fasting period itself. When food is reintroduced, digestive enzymes are released, insulin levels rise, and nutrient signaling shifts from conservation to growth. Cells that have prioritized repair over proliferation respond rapidly to nutrient availability. From a cellular perspective, refeeding acts as a signal for regeneration. Stem cells that remained quiescent during fasting are activated in response to nutrient influx. Glycogen stores are replenished. Protein synthesis resumes. Metabolic pathways recalibrate to accommodate abundance after scarcity. This transition underscores why fasting cannot be evaluated in isolation. Its physiological effects are inseparable from recovery. When refeeding occurs gradually, the body integrates nutrients efficiently, reinforcing the adaptive processes initiated during fasting. When it occurs abruptly or excessively, the system may experience stress, as metabolic pathways shift too rapidly from conservation to storage. These observations highlight a broader truth. Biological systems favor modulation over extremes. Taken as a whole, the 72-hour fasting response does not reveal a body in decline, but a body in reorganization. The narrative is not one of deprivation, but of reprioritization. In states of abundance, the body emphasizes growth, reproduction, and storage. In states of scarcity, it emphasizes efficiency, repair, and preservation. Health depends on the ability to transition between these modes, not to remain locked in either. Modern lifestyles often reduce this flexibility. Constant caloric availability keeps insulin chronically elevated. Repair mechanisms remain suppressed. Inflammatory signaling becomes persistent. Over time, the metabolic system loses its ability to switch states smoothly. The result is not immediate illness, but gradual dysregulation. Understanding prolonged fasting through this lens reframes the conversation. It is not about endurance, discipline, or moral restraint. It is about biological rhythm. It is about recognizing that the human body evolved not for constant stimulation, but for fluctuation, periods of input followed by periods of rest. The most important insight is not that fasting is necessary, but that adaptability is essential. The body's capacity to reorganize under changing conditions reflects an underlying intelligence shaped by evolution. Appreciating this intelligence encourages a more nuanced understanding of health, one grounded in physiology rather than fear.